This project is about Baldwin Hills Reservoir failure. We're gonna cover geological engineering aspects of it. I am Sharif Abdulaziz and I'm working with Martha Jomaines in this project that we are submitting to Dr. Matthew Malden for the geological engineering class at Virginia Tech for fall 2010.
Baldwin Hills Reservoir and its supporting dam were located about 8 miles from Los Angeles City Hall in Southern California. Los Angeles Department of Water and Power spent 4 years in the construction of this water supply facility starting in 1947. Only in 1951, the Baldwin Hills Reservoir became in operation. The reservoir capacity was 897 acres with an estimated surface area of about 20 acres. As part of the description of this facility, it was found that a high dam of 230 feet was used to impound the water inside of the 650 feet wide reservoir. Geology at the location of the Baldwin Hills Reservoir, which is shown with the red line in the figure. The formation of the Baldwin Hills is related to two main geological processes. The first one, folding. As you can see in the figure, the blue line shows the Inglewood anticline. The second main process is faulting, which is represented with the two green lines. As consequence of the interaction of this process, the preliminary anticline of these chains of hills has been modified by deep slip displacement along the Inglewood Fault. The geological origin of this Inglewood anticline is attributed to the drag fall during the formation of the thick marine sedimentary section overlying the Newport Inglewood area during the Tertiary and Quaternary strata. Complementary to this folding system, the predominant vertical progressive movement was tracked through the striations of the faulting surface. The soil stratification is composed of different layers of low plasticity clay and silty sand layers. Generally speaking, this is a soft, sandy foundation rock.
Design of dam foundation and seepage control. Baldwin Hills Reservoir and dam were constructed on ruptured soft sandy foundation rock. Therefore, water cutoff system was used underneath the reservoir and its dam. The selected water cutoff system consisted of 4 different layers on top of the rock foundation. These layers are, as shown in the figure, an asphalt lining, a gravel drain basin, compacted clay layer, and a final asphalt layer. The top asphalt layer was used to prevent the water inside the reservoir to penetrate through ground fractures. The underlying compacted clay layer was selected to be a second defense line against water penetration. The gravel drain basin was mainly used to prevent piping in case of water flow. The bottom asphalt lining was used to control water flow through gravel basin rather than percolating into rock faults. The system was used to provide what was considered a margin of safety against piping as well. As will be seen later, the system was a trigger factor for the failure of Baldwin Hills Reservoir and Dam. This video shows a live streaming for the failure of Baldwin Hills Reservoir and Dam that took place in December 14, 1963.
Camera crews from TV station KTLA arrived at the reservoir and began to broadcast live aerial pictures of a disaster in the making.
And right here now, as we come up over the Baldwin Hills Reservoir, we can see the main break in the reservoir itself. The reservoir.
While workers desperately tried to repair the breach, water began to flood the streets below. As the LAPD continued to evacuate the valley, the leak in the dam's face became a torrent.
There goes a large chunk of the inner cement here in the Baldwin Hills Reservoir. That hole is 50 feet across.
For the first time in American history, aerial pictures of a disaster were being broadcast live on television. At 3:38 p.m., just 4 hours after the first sign of trouble, the Baldwin Hills Dam gave way.
So the question now is, what are the causes of failure? It is believed that water flow underneath the reservoir and its dam was a direct reason for the deterioration and erosion of the foundation soil. However, it is also believed that the water was never to flow and produce failure if the lining system did not crack. The lining system cracked due to movements along the reservoir fault. Therefore, the main causes for the failure of Baldwin Hills Reservoir and Dam were attributed to the causes of such movements. 3 different theories attempting to explain possible reasons for generating fault movements along the reservoir fault were proposed. These 3 theories are the tectonic theory, the subsidence theory, and the subsident fluid injection theory.
This theory is based on the records of recent surface rupturing along the known active faults and on indications that the sense of the contemporary movement appears to be indistinguishable from that of prior displacements. According to the theory, movement along faults at the Baldwin Hills Reservoir locations were a result of the large vertical movement along main faults, which is represented by the Inglewood fault with the green line. 2 major objections to this theory were: first one, general displacements along the subsidiary faults occurred in response to relative great displacements along the principal fault, which in this case is the Inglewood fault. No evidence has been produced to indicate creep rupture or cross-strain that would increase the displacement along the Inglewood fault or near major faults in the Baldwin Hill. The second objection refers to the margins of the near surface on-grapping anticline fault should move outward away from the fault axis, but surveys for benchmarks situated on the fault of the anticline show in the ground to be moving toward the anticline axis, as can be seen with the red arrows in the figure. The second theory is the subsidence theory. This subsidence came from the oil extraction, which started in 1924. Supporters of the subsidence theory argue that the 6 feet or more of grab subsidence in the Inglewood field is related in space and time to the net withdrawal of the 67,000 acre-feet of oil, water, and sand from the shallow producing horizons. The oil field occupies an irregular oval area that extends diagonally across the trend of the hills along the axis of the faulted Inglewood anticline. In the figure, the yellow area shows the oil field. The red area refers to the location of the Baldwin Hills Reservoir. As a support for this theory, almost all the observed surface rupturing has occurred on the edge of the subsidence bowl. Stretching on the ring of the sagging round surface is obviously a mechanism of proven consequence of the subsidence and tension cracking of the near surface materials. In this figure, the red line represents the oil field and the blue line represents the locations of the Baldwin Hills Reservoir. According to the subsidence theory, the down drag and stretching pressure volume will be distributed along the ring of the subsidence area, shown with the orange line in the figure. In objection to that, almost all the rupturing has occurred in one limit section of the Baldwin circumference, which is shown with the purple line.
As shown earlier, fault movements cannot be explained using the tectonic theory or the subsidence theory. The subsidence fluid injection theory provides a feasible reason for fault movements in the vicinity of Baldwin Hills Reservoir. This theory is based on the fact that oil pressures within the oil field decreased with time, which reduced the production rate. Therefore, change in the oil extraction program was started in 1954, which included water flood program. The water flood program involved injection of brine into the oil-carrying permeable layer at pressure gradients in the range of 0.5 to 0.9 psi per foot. The figure to the left shows different faults, including the reservoir fault represented by the red line, and the location of Baldwin Hills Reservoir represented with the green line. Also, this figure shows different injection wells used in the water flood program. Before starting the water flood program, the deformation rate for Baldwin Hills Reservoir and Dam was within the expected range, which is shown with the green line in the figure. With the start of the trial operation of the water flood program, deformations started to occur faster, as pronounced in the change of the slope between the yellow line and the green line, because of the increase of pore pressures, which caused a decrease in the effective stresses and consequently decrease in the shear strength along the faults. Due to the success to increase the oil production rate during the trial of the water flood program, the full program with higher injection pressures was implemented. These higher pressures increased the rate of deformation significantly, as presented with the red line in the figure. This increase in deformation caused lining system to crack, which led to the final failure as explained earlier.
Lessons learned from this case history are: all the factors that may cause failure of the critical structures should be considered in the design, which was not the case for the Baldwin Hill Reservoir. It's not easy to consider large fault movement in the design of dams, which needs more investigation to address the issue within the design process. Appropriate line system from critical structures such as Baldwin Hills Reservoir should be selected given all the possible failure criteria. For dams, settlement and seepage strength should be tracked over time because they could provide an alert for serious damage. Better communication between parties involved in the design, operation, and maintenance is required.